And so last time we had some definitions. Remember, we were talking about geodesic metric spaces. And we made a definition that a geodesic in such a space was D strongly contracting if it satisfied this property that if ever I have 2 points in the space and the distance between them is less than the distance from one of them to the geodesic, that was this infeasible distance from y to the geodesic, then when I take the closest point projections of those 2 points, they can't be too far away from each other. Okay? And remember, the closest point projection is officially defined as like a set. You could think of it like a point. It doesn't matter anyway. So I want the diameter to be bounded by this D, uniform number D. Okay? And we saw some examples last time that in the hyperbolic plane, it turns out every geodesic is 2 strongly contracting. And in a tree, every geodesic is 0 strongly contracting. Okay? But in the Euclidean plane, geodesics are only strongly contracting if they're finite. You know, if you have a finite length geodesic, then obviously you can just take D to be the diameter of the geodesic, and then you win. Okay, but any infinite length geodesic won't be strongly contracting there. Okay, so that's one definition. I want to mention another property that we're already kind of familiar with. Let me formulate it as follows. A geodesic gamma is Morse if whenever you pick numbers k and c, there exists some other number n, which really is a function of k and c. So I have some kind of function hanging around n of k and c, such that for any k, c quasi-geodesic, with endpoints, let me call it like so, I guess. Okay, so my quasi-geodesic is called rho, and I want its endpoints, rho of A and rho of B, to lie in my geodesic gamma. So it's some quasi-geodesic that starts and stops on gamma. Then we have that the Hausdorff distance between gamma and rho is at most n. Okay, so remember the Hausdorff distance, well, let's see, first of all, I'm kind of being bad with my notation and writing rho for the image of rho, so like thinking of it as like a subset of x. And the Hausdorff distance, remember, was talked about in one of the student talks, is the infimum of numbers such that rho is contained in the neighborhood of gamma, and gamma is contained in the neighborhood of rho. Well, maybe like formulating this is like a little, so gamma, I guess you might imagine that gamma is like this, and then rho is kind of like that, and then obviously the bits over here don't lie close to rho. So maybe I should really say like restricted to like AB, like just the bit of the geodesic between the points where rho starts. Okay, so I just care about this bit of gamma here. Maybe I'll call that gamma restricted, and this bit of rho. Okay, all right. Hope it's clear what I mean. Okay, all right. So that's a Morse geodesic, and we call so there's the secret kind of function hanging around n. So what is n? It takes 2 numbers, and it gives you a number. Okay, so we call this a Morse gauge. Okay, so a function's Morse, a geodesic is Morse if there is some function n like this called the Morse gauge for it, so you have this property. Okay, and we saw in the student talks, very nice proof, that in a hyperbolic space, in a hyperbolic space, there exists a Morse gauge n, some function, such that every geodesic is n Morse. Okay, by saying n Morse, I mean it's Morse with that function as its gauge. Okay, so that was the proof we saw before, right? You've given delta, then given any k and c, you can find some other number with this property. Okay, all right. So there's some connection between this Morse property and being a hyperbolic metric space. Hyperbolic metric space implies everything is Morse. It turns out that this other property, strongly contracting, also implies that every geodesic is Morse. So let me formulate that. Okay, so here's an exercise. For all d, there exists a Morse gauge n such that every d strongly contracting geodesic is n Morse. Okay, so you give me a number d, I can cook up some function n like this with the property that any time you have a d strongly contracting geodesic, it also happens to be n Morse. Okay, and I want to emphasize that this is in any geodesic metric space. Okay, so I'm not assuming that the space is hyperbolic. I'm not assuming anything about the space, and the same function n will work wherever you are. Okay. All right, so I put that as an exercise, but I thought I'd kind of give you the idea of it, and then you could maybe think about the details on your own. All right, so here's the idea. Okay, so the idea is basically the following thing. If rho gets too far away from gamma, then projecting to gamma shrinks distances too much. Okay, so that's the idea, and then there's a picture. So what do I mean by that? So, so that's the whole point of strongly contracting geodesics, right? If I have my geodesic, and if I have a ball that's disjoint, then when I project down, it's like things that were this far apart go to D. But if I make my ball farther away, so that's like maybe this is a ball of size 10 that shrinks down to D. Or I can make like a really big ball, and now this is a ball of size 1,000,000, but it still shrinks down to size D. So by going farther and farther away, the amount that I'm contracting gets better. Okay, so that's the idea. So now let me just draw the picture. Okay, here's gamma, and then I have rho, like so. Okay, there's rho, my nice quasi-geodesic. All right, and I want to like be far away, because when I'm farther away, I win more by shrinking. So I pick some kind of number like this, a cutoff number. That I maybe think of in advance, or you figure out what that number has to be. And then you say something like this. Well, what if I'm worried about my rho getting farther away than this number? Like if it stayed less than this arbitrary number that I picked, then I would be happy. Okay, it would be in the Hausdorff distance. Okay, so suppose it's far away. Well, if it's far away, then what I can do is I can take big jumps, because like this is like m, so I can take kind of jumps of size m, like so, big jumps, and each jump of size n like projects down to something of size d. So this is like m, and this is like d. And I pick m to be a lot bigger than d, so that this is like getting way smaller. Okay, so I have like 4 balls here. So up here it was like, like so. Up here it was like 4m, and down here it's like 4d. Okay, so what does that say? That says like, oh, like it used to be like this was a path of length like 4m, but now I could just go m, and then like 4d, and then m. And if you like pick the constants right, it's like m plus 4d plus m will be a lot less than like 4m. And that'll like mean that like, well, this path wasn't a quasi-geodesic, because this path is like way shorter. Quasi-geodesics can't be like too inefficient. Okay, so that's like the idea. Right? Anyway, so then the exercise is for you to work out the details. Okay, great. Okay. All right, so it turns out, so what have we seen? That hyperbolic implies things are Morse. Strongly contracting implies things are Morse. In fact, all three of these things are related in the following way. For X, a geodesic metric space, the following are equivalent. One is that there exists some delta such that X is delta hyperbolic. Two is that there exists some number d such that every geodesic in X is d strongly contracting. And three, there exists a Morse gauge. Oops. Which one do you do first? Get gauge n such that every geodesic is n Morse. Okay, so in particular, I want to highlight that like these first two are the same. So this definition we had of hyperbolic before, all triangles were delta slim, it's equivalent to every geodesic being contracting for some uniform number d. Okay, and we saw that both of these hold in hyperbolic space. So if you believe this theorem, then I wouldn't have even had to draw you the picture before, and you would have just already known that geodesics in hyperbolic space were contracting for something. Okay. Questions? Any questions? Okay, so let me. I made some more exercises to like work out the details of this, but I want to give you again the sketch of what's going on here. So let me do that. It's just very nice kind of simple arguments. So where you can see how these properties all get used and are related to each other. Okay, so here's the idea. Okay, so first, 1 implies 2. I want to assume that all triangles are delta slim, and I want to convince us that, in fact, all geodesics are going to be strongly contracting for some number. Okay, it's for some fixed number d. All right, so the first observation is that, well, the hypothesis is that all triangles are thin, but it's kind of easy to see that all quadrilaterals are also thin. Okay, why is that? If a quadrilateral, I just mean, 4 geodesics in a cycle like that. And the idea is, what do I mean? I mean on every side, each point on any side is within 2 delta of one of the other 3 sides. That's what I mean, just like before. And why is that? Well, I just make it into 2 triangles. Okay, I use the thing twice. Okay, very good. All right, so that's something. So now here's another observation. So I'm assuming my space is delta hyperbolic, right? So say that gamma is a geodesic, and I have 2 points. So I'm trying to prove the strongly contracting thing. So I take 2 points, y and y prime, and let's suppose they have the property that when I project them, I get something bigger than 10 delta. Okay, I just have any 2 points where their closest point projection is bigger than 10 delta apart. Okay, so then what does my picture look like? Here's gamma. Here's y. Here's y prime. And here I go down. Here's like the closest point projection of y. And here's the closest point projection of y prime. Okay, and I want to know what does the geodesic from y to y prime do? What does the picture look like? Okay, does it look like, I mean, it could look like anything, I guess. I don't know. You know, what I want to say is that it doesn't look like that. It doesn't get to go far away. OK, so why is that? So what I'll do is I'll pick a point in the middle. OK, so what's the point of being in the middle here is that if I now draw I now have a geodesic quadrilateral, and this point Z is close to somebody. That's the rule. He has to be within 2 delta of somebody on one of the other sides. OK, so let's think about, could he be close to somebody over here? OK, so what would that mean if he was within 2 delta of somebody over here? Well, maybe a thing to notice is that since this is a closest point projection of y, and this is a geodesic, this is also a closest point projection of this point. OK, so if the distance here was less than 2 delta, then the distance here has to be less than that, because this is a closest point projection. So that's also less than 2 delta. So this distance would be less than 4 delta. 4 delta is less than half of 10 delta. So if I'm in the middle, I'm more than 4 delta away. So this is not allowed. Very bad. OK? Jeez. OK, so I'm not over there, and I'm also not over here. So that means I'm close to somebody on the top. That means the geodesic really goes like this, and there's somebody here. OK? All right, so what does that tell me? Well, the distance now, maybe I'll get a W, from y to y prime is at least as big as the distance to W, because W is on the geodesic. So what does this say? This says that the distance from y to y prime is at least as big as the distance from y to W. Well, the distance from y to W is at least as big as the distance from y to z minus 2 delta. And the distance from y to z is bigger than the distance to the geodesic. OK? Because z is a point on the geodesic. All right, so what did we show? We showed kind of the other way around. We showed that if it's too big, then the distance is bigger than this. That's like the contrapositive of what we wanted almost, right? So what did we see? That dy y prime, if it's less than this number, OK? So we concluded that y prime is bigger than this number. So if that's not true, if it's less than that, then this assumption from before has to be wrong. So that implies the diameter is at most 10 delta. OK? And this is almost what we wanted, right? We just didn't want this 2 delta here. OK, so then you have to think about how you can get rid of the 2 delta. OK, it doesn't really matter. All right. Any questions? OK, so that's very nice. In a hyperbolic space, in fact, every geodesic is strongly contracting. And you can get rid of the 2 delta. So that was 1 implies 2. 2 implies 3. We already did. That was my picture over here. OK? Or that's, you still have to think about it on your exercises. OK, so before doing 3 implies 1, here's another lemma. OK, this is, again, in any geodesic metric space. Gamma a geodesic, and y any point. And let's pick z in the closest point projection of y. OK, so my picture looks like this. Here's gamma, here's mystery point y, and here's z. OK, so then I can take the geodesic, the following thing. I can build a path that does this geodesic and then goes out that way. OK, so there's a geodesic from y to z, and then I could just go along gamma. All right, so So let me call this maybe, so here, maybe I'll call this like gamma 0 and gamma 1. So I'll break up my geodesic gamma at the point z, and then I'll have the concatenation of this geodesic from y to z with half of gamma. Is it clear what I mean? So this, all right, so I'll take this path. And the lemma says that if I do this, anytime I do this, if I take this concatenation to z and then I go like this, I get a quasi-geodesic. In fact, it's a 3, 0 quasi-geodesic. Okay, does it make sense what I'm claiming? All right, and I mean like parameterize this path in the usual way. Like this is parameterized as a geodesic, and then I parameterize that as the geodesic. Okay, they're both geodesics. Okay, so that's an exercise for you to prove. Okay, that this works. All right. But that's my claim. Anytime I do this kind of closest point projection, then go that way, I always get a quasi-geodesic. All right. So now that we did that, we can finish our theorem. So 3 implies 1. So what are we assuming now? We're assuming that there exists a Morse gauge such that every geodesic is n Morse. Okay, so what do? Let me set delta to be the Morse gauge applied to 3, 0. Right, I'm assuming there's some one fixed function like this such that that works. So in particular for 3, 0 quasi-geodesics, there's some number that they always stay within that number of any geodesic that they start and stop at. Okay, and now what I need to do is prove that triangles are delta thin. So let me draw a triangle. Good. Okay, so what do I need to show is that every point, say on the bottom geodesic, is within delta of one of the other two sides. So I draw this picture. I take this point, I do the closest point projection here, and then I go like this. It's a 3, 0 quasi-geodesic. Right? That's what our lemma says. And it starts and stops on this side. So therefore, the whole thing lies within delta of this side. Okay, in particular, all the points over here lie within delta of somebody over there. That only does this half, but there's the other half. I could just go the other way. So then I also do this. It's also a 3, 0 quasi-geodesic. Any point over here is with delta of somebody on that side. So every point on the bottom is within delta of somebody, and I won. Okay, that's the proof. Very simple. Okay, so maybe the point is that just emphasize that this is a 3, 0 quasi-geodesic, and this is an n Morse geodesic. That's our assumption that every geodesic is n Morse. Okay, all right, so that's my proof. Great. Any questions? Okay, so these are all like very related concepts, and in fact, having all your geodesics be strongly contracting is the same as being hyperbolic. I guess I want to emphasize that. So we saw that if a single geodesic is strongly contracting, then that geodesic is also Morse. The converse to that is false. So it's not the case that if a geodesic is Morse, then it's also strongly contracting. But what this says is if every geodesic is Morse with the same gauge, then in fact it's contracting. So that's a stronger statement, okay? But you should think that the contracting thing is better than the Morse thing. Definitely better. Okay, so what is the upshot of all of this discussion is that, now, like in this thing, like the hypotheses were like, everything is, all triangles are good, or all geodesics are contracting, or all geodesics are Morse. But you could now maybe weaken that and not care if everything is good, and maybe only some things are good. Okay? So the point is you might have a space maybe that isn't hyperbolic, but perhaps in that space there still exists some like contracting geodesics, and maybe you can use them to do good stuff because we saw they're nice. Okay? So here's the upshot. is that strongly contracting geodesics behave like geodesics in a hyperbolic space. In particular, anytime you have a strongly contracting geodesic, it's Morse, so it satisfies the Morse property. Okay, that's nice. So even if your space is not delta hyperbolic, you wish it was, but maybe it wasn't, maybe it still has some of these guys. It may have some strongly contracting geodesics. Okay, and if it has them, they might be useful for doing some things. Okay, so that's the point. Okay, any questions? So let me give an example of a space where this kind of phenomenon happens, where some things are strongly contracting, but not everything. Okay, let's look at the group G with this presentation, A, B, C, where A and B commute. And they don't commute with C. Okay, so this is, if you want, the fundamental group of a gadget like this, where I take a torus, and then I wedge a circle. Thank you. Okay. All right, so this is a group generated by ABC. A and B commute, C doesn't commute. That's the, if you want, the free product of Z2 with Z. And Van Kampen's theorem says, that's the fundamental group of this gadget. Okay? All right, so this group is not hyperbolic. Okay, you can kind of see that it has this copy of Z squared in it. It turns out that having Z squared as a subgroup means you can't be hyperbolic. Okay, that's we saw that Z squared itself is not hyperbolic, but it turns out that stops anything else from being hyperbolic. Okay, but I claim that the following, so G is not hyperbolic. Okay, we also know that G is, quasi-isometric to X tilde its universal cover. It's just some finite complex. And I claim that in this universal cover, I do have some good strongly contracting geodesics. So what does the universal cover look like? Let's see if I can draw it. Maybe I'll draw it this way. Is that good? That's probably good. Okay, so like the universal cover of the torus is some gadget that looks like this. It's a plane. Okay? And then at every integer point in the plane, I have this extra circle coming off, and that like opens up to like a geodesic. So I have a bunch of these, or like a line, right? So I have a bunch of these. And then I could go around the circle. If I go around the circle, there's another plane there. Every time I go around the circle, there's a plane. And then I could go here, and there's another plane. Okay, and over here, there's a plane. There's just a bunch of copies of planes glued together with edges. Okay, so that you can kind of see what it looks like, right? And it's not hyperbolic because I have this Euclidean plane sitting on the inside. Okay, well, let's consider the following kind of gadget. Let's see. I guess I want lots of them. Okay, so I have a lot of these things. And so let's do the following kind of path. So I'm going to go along an edge, and then I'll just go like up, and then I'll go along an edge, and then up, and then an edge, and then up, and an edge, and like so on. Okay? So if you are thinking of this as like the Cayley complex of your group, then this is the bi-infinite path, say, that looks like A, C, A, C, A, C forever. Okay, so I just do an edge in the torus, and then I do the C, and then I do an edge in the torus, and then I do a C. And that gives me some bi-infinite path in this Cayley complex. Okay, so I claim that this is one strongly contracting. Okay, and why is that? You can kind of see why that should be. If I can draw, yeah. Let's think about why that is. So I need to find a ball disjoint from this path. Okay, so this path, like maybe let's think about here in this. So the path goes on this edge, and then it goes this edge, and it goes that edge. So let's suppose, so if I have a ball, it can't touch this edge and it can't touch that edge. So it has to live kind of somewhere else away from this. So it has to kind of live maybe in this plane, or it could live like hanging off on this plane over here. That's all fine. You know, it could live, you know, wherever. So I could have a ball that lives in all of this junk down here as long as I don't touch the red thing. Okay? But if I think about what's the fastest way to get back to the red thing, well, I have to go into this plane. And then when I project onto this plane, the closest geodesic is just, the closest point is just this one edge. It has diameter 1. Okay, so any ball at all I take, this disjoint, if I project it, it's going to land inside this one edge, which has diameter 1. Okay, so it's 1 strongly contracting. Can you see that? All right, so this is an example of a space that's not hyperbolic, but still has these strongly contracting geodesics in it. Okay? All right, so that's a nice feature that we're going to come back to tomorrow. Yeah?
If you have a geodesic which is made of alternating segment in the line and in the plane, and if the length of the pieces in the plane is uniformly bounded,
Yeah. So this I just picked a particular kind of nice periodic thing, but Pierre is saying you build any path that, so I'm doing like, you know, these little edge pieces and pieces in the plane. As long as every time I do a piece in the plane, it's uniformly bounded. Say at most, here it was bounded by 1. Say you bounded it by 100, that's fine. Do anything where I only take go distance 100 in the plane, then that will be 100 strongly contracting. Yeah, make sense? Okay, very good. All right, so we spent all this time talking about hyperbolic stuff. We have all these student talks on it, and I want to spend a little bit of time, at least, like why, you know, who cares? Like what, you know, we have these hyperbolic groups. What's, you know, maybe what's nice about a hyperbolic group, okay, or hyperbolic space. So to that, I want to have one more kind of concept. A map is an L local geodesic if restriction to each length at most L subinterval of I guess I didn't say I is, as usual, an interval in R. Okay, so if restriction to each length less than L subinterval of I is a geodesic. Okay, so another way to say that is just the distance from gamma s to gamma t should be equal to s minus t whenever s minus t is at most L. Okay, whenever I pick 2 points that are within L of each other, then I want that to be actually the right distance in the space. So that's an L local geodesic. Okay, so here's a lemma that I guess I'll prove. But in a hyperbolic space, every local geodesic is a quasi-geodesic. And I mean like in the usual way where you pick a number L. If you have an L local geodesic, then there's some other numbers K and C, such as a KC quasi-geodesic that depend only on L, right? Okay. Let me give an example. Maybe I can write it a little low here because it doesn't really matter. But like, so in R2, say with the L1 metric, that's the taxi cab metric where it's like you imagine it was a grid and geodesics go like straight and make turns. Okay, so in there, what does a geodesic, you know, what might a local geodesic look like in this space? Well, I could just go for a while and I could turn, and I could go for a while and I could turn and I could turn, and as long as I make big chunks between every time I turn, that will be a local geodesic. Okay, so this is a local geodesic. Okay, of something like that. Notice that that is not a quasi-geodesic. You know, because if it's a quasi-geodesic as I go, I'm supposed to not come back to where I started, because like the distance, so like this might be like parameter 0 and also parameter 1,000,000, and so the points are supposed to be far from each other, but they're the same point. Okay, so this is a local geodesic, but it's not a quasi-geodesic. So this is again not an example. Not an example in R2. Right? So that's a.
In the lemma, the constant for the quasi-geodesics on delta and delta.
Yeah, I'll prove it. Yeah, I'll prove the lemma, and then you'll see. Okay. All right, but this is an example of a space R2 with the L1 metric. Well, we know it's not hyperbolic, and it doesn't have this property of the lemma because local geodesics. And I can make this picture where it's local for whatever number you pick a number, and I can draw this picture where it's L local geodesic. Okay, and it's not going to be quasi-geodesic. Okay, so let me prove the lemma. And in the proof, you'll see how the constants work. Right. Given delta, let n be the thing for 2, 0 quasi-geodesics. Okay, so we know in a delta hyperbolic space, every geodesic is Morse for some thing. So there's some given quasi-geodesics 2, 0, there's some number such that any 2, 0 quasi-geodesic stays close to any geodesic. Okay, so we know that such a number exists. And I'm going to take L. So this is the Morse constant for 2, 0 quasi-geodesics. Okay, and I'll take L such that L over 4 is bigger than 2n plus 2 delta. Okay, so here I'm picking L. Right? And I claim that, write it down. Every L local geodesic is a 2, 0 quasi-geodesic. Okay, so you see, given delta, I picked a number L. Any L local is 2, 0. You could pick L to be different things, and you would get different numbers. Is what you pick, right? Like if you wanted, if you wanted this to be, like you're not going to get like a 1, 0 quasi-geodesic. That's a geodesic, so that's not true. But you could, I think, get as close to like 1, 0 quasi-geodesic because you want it by letting L be bigger. You'll see how the argument works. Okay. All right. So that's the claim. What do we need to show? All right, so I claim I'm going to now assume that I have an L local geodesic like this, and I want to prove it's a 2, 0 quasi-geodesic. All right, so what do we need to show? That the distance is greater than or equal to a half times the distance for, let me assume s is less than t so that I don't have to do absolute value. All right, so I'm going to assume t is bigger than s, and I want to show it's bounded below by that, and I also need to show it's bounded above by, 2, but this is immediate. So I'm not going to worry about that, because that just comes from like the triangle inequality. I just move along my geodesic, and I do a triangle inequality, and I get, sorry, okay, like that. Okay, fine. And so it's true without the 2, right? My point is like that's true, okay, just from the triangle inequality, which is better than I need. So I'm not going to worry about that. All right, so all I need to do is prove this thing here. All right, so I'm going to prove it by induction. So I'm going to induct on the length t minus s. All right. All right, so let's suppose that it holds for all t minus s less than some number r. Okay, so I'm inducting. And notice that the base case, it's true for r equals L, because that's the assumption. Whenever t minus s is less than L, then it's actually equal. Okay, so definitely the base case is true, and I'm assuming r is some number. Then I've proven the claim whenever t minus s is less than or equal to r. Right, and what I'll do is I'll show that it holds for, let's say, the next kind of chunk. Okay, so whenever t minus s is as big as r plus L. Okay? All right, so now we're just going to draw the picture and we're going to do it. All right, good. So here I pick along my thing. Really long. Good. Okay, so here's gamma of s. And let me call that, just for fun, x. And here's gamma of t, and let me call that y. All right, so I'm assuming I have some t and s, again, where t is bigger than s with this property. OK, so what am I going to do? Let me back up to this point. I'll call it w, which is gamma of t minus L over 2. So I'll back up L over 2. OK? And then yeah, I hope I didn't mess up my constants. Oh, that's OK. Is that OK? Let's see. Maybe I'll only, yeah, I think, well, it doesn't matter. Maybe I want to assume that. Maybe I'll only take a step of size L over 2. OK, maybe that's what I want. All right, so then let me back up another L over 2 to a point here, which is gamma of t minus L. OK, and now let me draw the following. Oh, yeah. Yeah, that sounds good. And now let me draw a picture. Well, I already drew a picture. All right, so I'm going to take I want a geodesic triangle. Where's my geodesic triangle? Here's one side. I take the geodesic. Notice that from here to here is a geodesic, because that's length less than L. That's the assumption. It's an L local. So this is already geodesic. Whew, good. OK, and then there's some geodesic over here, like so. OK? All right, so what do we know? We know many things. First of all, this is a geodesic triangle, so W is close to somebody. It's within delta of somebody. And I want to know if it's over here or over here. OK, so let's first think, what if it was close to somebody over here? Let's think what would happen then. Well, this is a geodesic. Very good. This is, by assumption, since L, t minus s is less than this, if I subtract L, then I'm definitely back in the territory where I've already proven the claim. So this is a quasi-geodesic, a 2-0 quasi-geodesic. So every point on here is within n of somebody over here. Right? Does that make sense? This restriction is a 2-0 quasi-geodesic. So I have my Morse constant for 2-0 quasi-geodesic, so it's close to somebody over here. Right? So if this was close to somebody here, then it would be n plus delta away from a point like this. OK? But, oh, look, this whole restriction is also a 2-0 quasi-geodesic all the way out to W, because I subtracted L over 2, and that put me in my happy range. OK? So the distance from this to any point over here is at least a half of the time distance. But what's the time distance? This time distance is equal to L over 2. And this is more than that. So this purported point, W prime, what do I know? The distance from W to any point over here is at least half of the time distance to W, which is at least the time distance to W is bigger than this time distance. So that's like a half L over 2. That's L over 4. We chose that to be bigger than 2n plus 2 delta. So it's bigger than n plus delta. OK? So it can't be close to a guy over there. Not allowed.
Wait, I will just, so you think that it's a quasi-geodesic from S to T minus L over 2?
I'm using, yes, I'm using that it's a quasi, so the restriction from S to this point, T minus L over 2 is a quasi-geodesic. Oh, I'm assuming I've proven the claim whenever I have 2 points distance at most r. And Now I'm assuming that t minus s is at most r plus L over 2. So if I subtract L over 2, then the distance is at most r, which is the situation that I've proved it. I changed it, sorry, yeah. OK, does that make sense? So I'm assuming all the way from here to here is a 2-0 quasi-geodesic. So that lets me estimate the distance from here to here as at least it's greater than or equal to half times the time parameter distance, which is bigger than L over 4. OK, so that's bigger than this. So that says that this thing doesn't happen. OK, so we can rule this out. Who cares? So that means W's friend is really over here. Ah, good. Let's call that Z. All right, so there's somebody Z down here that's distance at most delta away. Make sense? And now we're in business. OK, so now I have the distance from W to Z is at most delta for some Z on the geodesic from X to Y. So now let me estimate. I need to estimate the distance from X to Y from below. Right? That's what I need to bound. OK, well, it's equal to the distance from X to Z plus the distance from Z to Y, because Z is on the geodesic. OK? But the distance Z and W are close. So this is bigger than or equal to the distance from X to W plus the distance from W to Y minus 2 delta. Because I just switched from Z to W, that changes things by most delta. And I do it twice. OK? All right, so now what do we know? Let's again use our fun fact that it's a quasi-geodesic all the way from X to W. OK? So that says this is at least the distance. So the time difference from here is t minus L over 2 minus S divided by 2. That's what being a quasi-geodesic means. From W to Y is a geodesic. So that's L over 2, right? And then I have minus 2 delta. OK? Let me write L over 2 as L over 4 plus L over 4. OK? So now, look, this plus L over 4 kills that L over 4. So this is just equal to t minus s over 2 plus L over 4 minus 2 delta. This is a positive number, because L is bigger than 2 delta. OK, so I did it. All right. Good. So there we go. That's the induction. Very nice. Any questions? Yes?
So in the lemma, it would be like in a hyperbolic space, there is a LCK such that every L local geodesic is a CK quasi-geodesic.
Yes.
So not every local geodesic is quasi-geodesic, only the ones with
Oh, sorry. Yeah, yeah. So I lied. Every local with kind of with big L. Yeah, sorry. You need the local constant to be big depending on delta to get anywhere. That's right. Thank you. OK, good. So we did that. Very nice. All right. So now, finally, a little bit of nice consequence. Suppose that G is a hyperbolic group. Again, so here I'm thinking of S a finite generating set for G, such that the Cayley graph is delta hyperbolic, for some delta. So in a hyperbolic group, there exists some number L such that if I have a word, so this is a word in the generating set that's equal to 1 in the group. That's what I mean by this, OK? With each of these things in the generating set, then some subword of length at most L is not a geodesic. Meaning it's not the shortest representative of that group element. Okay, obviously, in this case, this word is not a geodesic word because the shortest representative of this element is just 1, which is length 0, but this has length n. And I'm just saying, if I have a word in my generators that happens to define the identity, then it has to be the case that some subword of bounded length L is not a geodesic. Okay, and that's like an immediate consequence of what we did. Just take L as above in our proof from before, the L local quasi-geodesic condition. Okay, and what does that say? If every, remember our geodesic metric space now is just the Cayley graph of this group with this generating set. Okay, so this is just some path. So if every subword of length less than L was a geodesic, that would mean this path in the Cayley graph was a L local geodesic. Okay, so if every subword of length less than or equal to L is a geodesic, then this path in the Cayley graph is a 2, 0 quasi-geodesic. So that implies the distance in my space from this product from the place I end up to 1 is at least n over 2. But it's supposed to be 0 because it's the identity. Okay, does that make sense? All right, so right away we see this nice property in hyperbolic groups that if you want to write the trivial word down in the generating set, you have to use, you can't have done it in like a local geodesic way. So this gives you an algorithm. For the word problem. All right, what is the word problem? You have a group with a generating set, and the problem is I tell you a word in the generators, and you tell me if it's the trivial word element in the group or not. Okay, that's the problem. And like in general, it's not solvable. Like there's groups where there's no algorithm that will solve it. In hyperbolic groups, there's a linear time algorithm that solves it called Dane's algorithm. Okay, and what's the algorithm? It's just do this. Okay, if you want to know if it's you have your word, you want to know if it's the identity, you just check all subwords of length L. See if they're geodesic or not. If they're all geodesic, then it's not the identity. If it is, if it's not geodesic, you just reduce. And then I get a shorter word and then I repeat. And every time the length of my word gets shorter, maybe eventually I get down to the identity, and then it's the identity. If I can't reduce anymore, then I know it's not the identity. Make sense? All right, so the algorithm is just look for subwords of length at most L that are not geodesic. If exists, if you find one, reduce. So replace that subword with a shorter word and repeat. If none exists, then your word is not the identity. That's the algorithm. Okay, and that's a linear time algorithm because you run it as many times as the length of your word. Okay, you can also see that from this that hyperbolic groups are all finitely presented. Okay, so given the generating set, there's a finite list of words in the generators that give you all of the relations. And what are they? You just look for words of length at most L over 2, at most 2L, that define the trivial element. And this, because if you think about what you're doing when you do this replacing, you're changing a word of length less than L with a word of length like less than L minus 1, so that, like I have this path that I'm replacing with that path, that's an element of length less than 2L. And that's the only things you're using to do the reduction. Okay, so the relation set, take just relators, all words of length less than or equal to 2L defining the trivial element. Okay, and that's a finite set because there's only finitely many words of length less than 2L, and your group is generated by that. Okay? All right, and then one other thing, maybe I'll just say, is that this is really saying that hyperbolic groups have what's called a linear isoperimetric inequality. Okay, let me not write down carefully what I mean by that, but if you have, for example, a finitely presented group, you could build the Cayley-2 complex for that group, where you take, edges are the generators, and I glue in a cell for every relator. And then given a loop that closes up, you could ask, like, that's null homotopic so if it closes up, that means it defines the trivial element in the group. So that means you can fill it in with disks. So you just ask how many relators does it take to reduce it to the identity. Okay, and you call that the area of the loop. Okay, so the isoperimetric inequality is relating the area of a loop. So I have some word like W, and I want to know what's its area. And this just says that the area of W is bounded above by the length of W. In fact, that's what the algorithm gives us. Because like how many relators did I need to use at most the number of elements, letters in W. Okay, so that's nice. Hyperbolic groups have a linear isoperimetric inequality, and it's a theorem of Gromov that if, let's just say, a finitely presented group has a subquadratic isoperimetric inequality, then the group is hyperbolic. Okay, so anytime you have a group, say finally presented, and you figure out like what's the worst inequality for any possible such word, if you can prove that for every closed loop W, it's bounded by some function that's subquadratic in terms of the length, then your group has to be a hyperbolic group. It has to, in fact, be linear. Okay. Of course, there are things with quadratic isoperimetric inequality that aren't hyperbolic, like Z2. Think of like what's the isoperimetric inequality for Z2? It's quadratic because of the area is like the square of the length. Okay. All right. So, but subquadratic implies hyperbolic. Very good. All right. Okay, so that's end the story for now about hyperbolic stuff. That's some cool properties of hyperbolic spaces, hyperbolic groups. And now I want to turn to kind of the last topic, which is about extensions. Okay, so in the title of the mini course, there's something like blah, 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 and then it says hyperbolic extensions. Okay, so now we want to come to think, what does that mean? What are extensions? What are group extensions? And when might they be hyperbolic, which is this stuff we've just been talking about. Okay? All right. So the kind of basic question is, how can we build new hyperbolic spaces? Out of old ones. Okay, it's like I want to do some construction process. I have a bunch of building blocks that are all hyperbolic, and I want to glue them together in some way, and I want the result to be hyperbolic. Okay, that's kind of the basic question. All right, so let me tell you a theorem in this kind of first theorem in this direction. This is called the Besvina-Fein combination theorem. Okay, this was from 92. I guess Besvina proved many things in 1992. Right, so it exactly kind of gives an answer to this question. It's not like an if and only, but it's like tells you one way that if you have hyperbolic things, you can glue them together. If you do it correctly, you'll get a hyperbolic output. Okay, So let's suppose X is a finite graph of spaces. We learned about those the other day. If I have some spaces, I glue them together in a graph-like fashion. Okay, this like Bass-Serre theory kind of thing, right? So I'm exactly in that situation. And let me suppose various things about these things. All right, so you should think that like these, like the spaces are like finite cell complexes, and I care about like when their universal covers are hyperbolic, right? Okay, so so let's say the universal covers x e tilde and x v tilde of the edge and vertex spaces are all delta hyperbolic. So I guess I mean that I fixed one delta. I guess there's only finitely many of the things, so whatever. If they're all hyperbolic, there'll be one delta that works for all of them. So I guess I mean like there's some like kind of metric on the universal cover. Maybe I like made my spaces out of cell complex, and each cell got some metric on it. Okay. Like maybe it's the Cayley-2 complex of a graph, of a group. Okay, let me suppose that the gluings, where I glue these gadgets in, are QI embeddings. Okay, so remember there's these attaching maps that I get when I build my graph of spaces. So that I lift that to the universal covers, and I'm just gluing these gadgets into those spaces, and I want that to be a quasi-symmetric embedding. Okay, so I want to do it in do the gluing in a way that respects the geometry. Okay, and then the third thing is that the flaring condition is satisfied. Okay, and I'm not going to write that down because it's sort of a mouthful, but we'll come back to it. All right, so I'll write something else about flaring in the future, and it's like basically the same thing as this, but I don't want to write it down. Okay, so it's some flaring thing that stuff has to basically it's like when I move in horizontally in my tree, and things have to flare. That's the rule. Okay, in some prescribed way. All right, so then the universal cover x tilde is delta Gromov hyperbolic. Okay? All right, so that's the theorem. And in particular, let me maybe mention special case, like as we saw in the talk the other day about Bass-Serre theory. Really, you should think that these graphs of spaces are like you built them because you were doing a graph of groups. Like I had some graph of groups where I had vertex groups and edge groups, and then I wanted to understand the groups, so I made spaces and I glued them in the right way. So this thing is really like you should think if I have a graph of groups, this is like the universe. This is like the Cayley-2 complex for that graph of groups. Okay, so this is really applying to graphs. And this first condition that the vertex and edge spaces will be hyperbolic, that just means the groups themselves are hyperbolic. So this applies to graphs of hyperbolic groups. Okay, so basically it's saying if I have some graph of hyperbolic groups, if I do the inclusion maps in a way that's a quasi-symmetric embedding, then as long as I satisfy this mystery flaring condition, the result will be hyperbolic. Because this is like a way to build new hyperbolic groups out of old hyperbolic groups. And let me just say,
one more condition, like the example of graph of spaces where every piece is hyperbolic, the embedding a quasi QI, and it's not hyperbolic.
Well, I put the flaring condition. I'm putting a bunch under the rug here.
Yeah, but I'm asking a question.
What's the question?
Is it true that the theorem is false if we don't put any additional condition besides?
Oh, if we get rid of the flaring condition? Yeah, then it's false. Yeah, for sure. Yeah, I mean like well, yeah, I mean, I guess I don't have a good example, but yeah, it's definitely false.
You could take Z2 as a product graph group. So
Yeah, I think you can write like a range to have a Z2 in your group in an easy way. Yeah. Okay, and let me just make one more comment. So this applies to graphs of groups, and the proof uses flaring to conclude subquadratic isoperimetric function, or isoperimetric inequality. So that's how the proof goes. Okay, so they use this flaring condition. They somehow, whatever it says, you look inside the space that loops, and by the flaring, you break things up into rectangles because they all flare. You can estimate their area in terms of the perimeter and prove that it's bounded above by a subquadratic function, and therefore Gromov says it's hyperbolic. Okay, so that's it's related very much to this stuff we were just talking about. Okay. All right, so this is kind of like the tool we want to use, maybe. I mean, we're going to use a related tool, but this says, you know, it is maybe possible sometimes to take hyperbolic groups and glue them together in ways to get new hyperbolic groups. Okay? All right, so now I want to look at group extensions. Okay, so for K and Q groups, okay, K used to be a number, now it's a group. Sorry. Okay. All right, an extension of K by Q is any group fitting into short exact sequence as follows. Like that. Okay, so I don't know if everyone knows short exact sequence. So a sequence is exact, so this is a sequence of groups. And to be exact just means at every stage the kernel is equal to the image. Sorry, well, yeah. Okay, is that what I want to say? Or the image, the image is the kernel. Okay, so like I have so this is like K, I'm mapping it into G, and then it's saying that K, that image of that group is exactly the kernel of this map. So Q is really just a quotient of G by this normal subgroup K. That's all it's saying. Okay, and notice that the image of this map is just the identity. So that says that the kernel of this map is trivial. So that's saying this map's injective. Okay, and the kernel of this map is everything, because this is the identity. So that says the image of this map is everything. So this is just saying that this map's surjective, that map's injective, and that Q is the quotient of K. All right, that's all it is. Okay, so just think like a quotient. I mean, it's like, I don't know. That's all it is. Okay, so the question, kind of just a more specific version of this before. So I think of this as like I have my groups K and Q, and I'm like combining them in some way to build G. Okay, so that's like the idea of an extension, some way to build, some group G out of K and Q. So if K and Q are hyperbolic, when is G hyperbolic? Okay, so that's the kind of question we want to now get at. Now that we learned about hyperbolic groups and that they're the best, we really want to build more of them. Okay? Okay, so the answer is kind of that it depends. So for example, I could do the stupid extension. That's what I just mean this thing. I could just take the product of K and Q, and that's an extension. And that's probably not hyperbolic. Okay, like in particular, if k and q have infinite, are infinite, then it won't be hyperbolic. Or if like there's an infinite order element in k and an infinite order element in q, then I have a z plus z in here, and it won't be hyperbolic. Okay, so this is never hyperbolic if, for example, my groups are infinite groups. Okay, and you should really only think about like when k and q are infinite, because otherwise the group in the middle is quasi-symmetric to the other one of them, because they have a finite quotient, like one's finite index than the other or whatever. Okay, so then like if one's hyperbolic, if the other one is. So this is like the interesting case. Okay, so it depends. It depends on how k and q are combined. So here I combine them in the stupid way, and then I didn't get something hyperbolic. So I have to do it like something kind of complicated. Okay? All right, good. So let me just say a couple comments about what I mean about how it has to be combined. So the short exact sequence induces what's called a monodromy, which is a map from Q to out of K. Okay, how does this map go? Well, what I do is I take something in Q, and I look over at my short exact sequence, and I say, aha, it was exact. Exact meant it was surjective onto Q. So I can pick somebody that maps onto Q. Okay, so I do that. And then notice that, so I pick something that maps onto Q, and then notice I now have this nice element in G. And K is a normal subgroup of G. So that means if I conjugate by anything in G, it sends K to itself, to finding some automorphism of K. So if I take Q here, I lift, and then I conjugate, I'm getting an automorphism of K. You can check that that depends on which lift you took. There's many lifts. But if I choose different lifts, they differ by conjugation by something in the kernel, which is an inner automorphism. Okay? So if I conjugate by a lift, then I'm not getting a well-defined automorphism, I'm getting a well-defined outer automorphism. So that's a way to take something here to build an outer automorphism that's well-defined, and that turns out to be a group homomorphism. Okay, that's called the monodromy. Okay, and maybe just, so I call this rho. And maybe let me just say that for G to be hyperbolic, kind of, by depends, I mean that like rho must be sort of complicated. Okay, so for example, if there exists something in Q and something in K of infinite order, such that this outer automorphism fixes the conjugacy class of K, then if I could just kind of think of a sub-extension by just taking the preimage of Q, and inside of there, that's like fixing K, and if you could think about what that means when I conjugate this element of Q by this lift of thing, it's not doing anything, so that means they commute, so I built a Z plus Z. Okay, so if that happens, then I get a Z plus Z inside of G, so it's not hyperbolic. Okay, so complicated had better mean this, that for the image of this thing, it can never fix, things can't ever fix conjugacy classes. Okay, so that's like one condition that we see. All right, so then, so I'll stop there. So kind of pointing at something that we need. And then tomorrow we'll finish up by kind of analyzing this more and then using the geometry out of outer space to build hyperbolic kind of extensions like this.